Hello, welcome to my video series of algorithms. This is part 5 of Module 2, Logic and Proof. In this video, we'll discuss the notion of argument form and the rules of inference. From the previous videos, we have learned how to construct and transform statements. We have learned that statements can be regular statements or quantified predicates, and they have unambiguous truth values. We have learned logical connectives to construct complex compound statements. We have also learned to use logical equivalence to transform and simplify statements. Now, in this video, we'll learn ways to organize statements into a sound proof or argument. Know that the main purpose of a mathematical proof is nothing else than a regular argument. That is, it tries to convince people of something. It works the same way as what a lawyer does in a lawsuit defense. Now, consider what makes a successful lawsuit defense. It must contain two parts. First, the lawyer must provide sufficient and solid evidence. Second, the lawyer must present this evidence clearly and logically. We can formalize these two components in mathematical proof. For the first part, we consider each evidence as a fact or a statement. To provide sufficient and solid evidence means that we need to provide a set of sufficient, relevant, and true statements. The ways to construct true statements can be found in the previous videos. For the second part, we need to organize the evidence or statements in a logical way. The organization of the pieces of evidence or statements is called argument form. A good or valid argument form should make it clear to people that if all pieces of evidence are true, then we know what needs to be proven is true. In this video, we will focus on discussing argument forms. Let's begin by introducing some basic notions. Consider a piece of proof or argument as a list of ordered sentences. Each sentence is a statement. All statements, except the last one, correspond to the pieces of evidence we provide, and they are called premises. The last sentence corresponds to what we want to prove. It is called the conclusion. The internal connections and logic that convert the premises to the conclusion is the argument form. We say an argument form is valid if and only if it can make the conclusion true when all premises are true. In other words, a valid argument form should bear logical equivalence to the statement P0 and P1 and all the way through Pn implies R. Here, the Pi's corresponds to the premises, and R corresponds to the conclusion. Based on definition, when we combine both true premises and a valid argument form, we'll obtain a sound proof or argument. To construct true premises, please refer to our previous videos in this module. We will discuss how to construct and verify valid argument forms here. First, recall that the definition of a valid argument form. When all premises are true, a valid argument form can make the conclusion true. Therefore, we can verify whether an argument form is valid using a truth table. We will simply check all the rows where the premises are true and verify whether the conclusion is also true. We'll give several examples below. Let's look at the first one. Show that the argument form P implies Q, P then Q is valid. We begin with analyzing the argument form and identify the premises and conclusion. According to definition, we know the premises are P implies Q and P. The conclusion is Q. Next, we will construct a truth table. We see that the elementary statements contained in this argument form are P and Q. Therefore, we will need 4 rows to enumerate all their truth value combinations. We also add columns that correspond to the premises and conclusion. Once we have finished filling up the truth table, we will check each row. We see that 2 premises, P implies Q and P, are both true for only the first row. Then, we check the truth value of the conclusion Q in the first row. We see that it's true. At this point, we can claim that, for this argument form, when all premises are true, the conclusion is true. Hence, it is a valid argument form. This argument form is also called modus ponens. Now, let's look at the second example. Determine whether the argument form P implies Q, Q, then P is valid. Similarly, we identify the premises as P implies Q and Q. And the conclusion is P. Then, we will construct the corresponding truth table. We see that in the third row, all premises are true, but the conclusion is false. Therefore, according to definition, the corresponding argument form is invalid. We also have more complicated argument forms. For example, consider the argument form P or Q implies R, P or Q, then R. We want to decide whether it is valid or not. Its premises are P or Q implies R and P or Q, and its conclusion is R. When constructing the truth table, know that we have 3 elementary statements, P, Q, and R. Therefore, we will need 8 rows to enumerate all truth value combinations. After filling up the table, we find that 3 rows correspond to the case where all premises are true. And we look at the truth values for the conclusions and verify that all are true as well. Therefore, we can claim that the argument form is valid. Similar to logical equivalence, we also have a set of pre-proven valid argument forms. They are called rules of inference. We will not discuss each of them in detail, but you're encouraged to prove their validity using the approach we presented above. Below, we list some important rules of inference. First, we have modus ponens, modus tollens, the rule of generalization, and the rule of specialization. Then, we have the rule of elimination, the rule of resolution, hypothetical syllogism, and the proof by division into cases. We can use these rules of inference to construct sound arguments. For example, say we have an argument, I drink either coffee or tea in the morning. I did not drink coffee this morning. Hence, I drank tea this morning. This proof uses the rule of elimination. P or Q, not P, then Q. The premises of this argument are I drink either coffee or tea in the morning, and I did not drink coffee this morning. You can see that if both premises are true, then we know the conclusion, I drank tea this morning, will also be true. This argument is a sound argument. Finally, I would like to emphasize that to make a sound proof, we need all true premises and a valid argument form. If one element is missing, we will not be able to make a sound proof. For example, see what happens if we have some false premises. Consider this proof. If -1 is positive, then -1 is larger than 0. -1 is positive, so -1 is larger than 0. You can easily identify the argument form of this proof as modus ponens, which is valid. However, one of the premises, -1 is positive, is false. Therefore, the corresponding proof is unsound. On the other hand, we also could have all true premises with an invalid argument form. Let's look at this proof. If a living organism is a human, it needs to breathe. A dog is not a human. Therefore, a dog does not need to breathe. You can see that both premises, if a living organism is a human, it needs to breathe, and a dog is not a human, are true. However, the corresponding argument form, P implies Q, not P, then not Q, is invalid. Therefore, the corresponding proof is also unsound. Okay, let's summarize this video. We have introduced the basic notion of argument form. We know that a valid argument form needs to make the conclusion true when all premises are true. And we can verify the validity of an argument form using a truth table. Further, to make a sound proof, we need two components. We need that all premises are true and organize them using a valid argument form. If we miss either part, we cannot construct a sound proof. In the next video, we will introduce some common proof techniques. Thank you for watching and see you next time.